In this recording, we'll overview our work entitled SHAIL, Safety-Aware Hierarchical Adversarial Imitation Learning for Autonomous Driving in Urban Environments. This work was presented at the 2023 International Conference on Robotics and Automation. To motivate our project, we note that many autonomous driving and robotics stacks implement safe, low-level, optimization-based controllers and rely on mid-level decision-making to select an appropriate low-level control scheme to execute. For example, in a roundabout, mid-level decision-making might choose between action primitives for whether to stop, yield, or accelerate into a roundabout, and then pass appropriate parameters into a controller that actually provide low-level steering and acceleration commands. As such, the goal of this project is to learn mid-level decision-making from only low-level data and a simulator, and to use the hierarchy to ensure safety. Our approach, SHAIL, combines hierarchical adversarial imitation learning with a layer for safety awareness. In our formulation for hierarchical adversarial imitation learning, given fixed, safe, low-level control options, which are sometimes called primitives or macro actions, we learn a high-level option selection policy whose goal is to match expert trajectories at the low level. For our safety awareness layer, we condition our high-level policy on predictions of controller safety. In this slide, we visualize the SHAIL methodology. In SHAIL, a learnable high-level policy and a safety predictor are combined to form a safe hierarchical controller. The hierarchical controller chooses from fixed option primitives that are reweighted online using their predicted safety. If the executing primitive option becomes unsafe, control is returned to the high-level option selector. Our controller interacts with a simulator built from real-world driving scenarios. A learnable discriminator differentiates between real-world expert low-level state action trajectories and the low-level state action trajectories that arise from following our hierarchical controller. Adversarial imitation learning is used to learn the parameters for the discriminator and the high-level policy while iterating through this process. For our imitation learning objective, we learn the high-level policy by minimizing the Jensen-Shannon divergence between the low-level state action occupancy measures using an adversarial imitation learning formulation. We still maintain the same low-level state action occupancy measure moment matching objective of imitation learning and show that we can put off policy gradients to the high-level policy with discrimination reward that is accumulated along each option. We augment hierarchical imitation learning with a safety awareness layer that predicts whether an option is safe or feasible online. We can use these predictions first as option termination criteria to pass back control from the primitives to the high-level controller, but also to condition that high-level controller on option safety. This augmented formulation allows for the integration of many other tools that exist for predicting controller safety. For our experiments, we built a simulator out of the interaction dataset of urban driving scenes where we control the ego vehicle along its path while other vehicles follow their recorded tracks. Here we show metrics displaying absolute performance, as well as metrics that compare performance between the simulated agent and the expert data. For absolute metrics, we compare the overall success rate and average travel distance. For comparison to the expert data, we compare the root mean square error in trajectories after 10 seconds, the average difference in velocity to the expert, and the Jensen-Shannon divergence between the distributions of accelerations seen. We compare against a simple rules-based model based off of the intelligent driver model, an off-policy data-driven model that does simple behavior cloning, an on-policy non-hierarchical model based on generative adversarial imitation learning or GAIL, and an ablated hierarchical adversarial imitation learning model without a safety layer. Overall, we demonstrate that SHAIL, even with very simple control options, provides superior absolute performance and similar comparative performance for both in-distribution and out-of-distribution testing. Finally, we show a scenario comparing the outcomes of the true experts. the rules-based model, and SHAIL, seeing that SHAIL looks more similar to the expert and is also able to use its safety layer in order to avoid a collision. In summary, we introduced SHAIL, a method for learning a policy that chooses primitives to match low-level trajectories. SHAIL combines hierarchical adversarial imitation learning with safety predictions, and in our experiments, it outperformed low-level driving imitation, even with very simple control options and collision predictions. Some limitations of SHAIL include that it relies on accurate simulation and is therefore only valid in those simulated settings, that it inherits the shortcomings of GALE, namely the instability of adversarial training and the low-dimensional feature spaces. It inherits the latency of safety checking methods that may be slow at predicting safety of executing option primitives. And in our work, it's limited to finite, discrete sets of options. Thank you for listening to this talk. We've made our source code open and available on GitHub for both the simulator that we used and the imitation learning algorithms that we used. And feel free to reach out with any questions.